Hello and welcome to lecture 22. This is NPTEL online certification course on aero engine gas turbine cycles. In last lecture we were discussing about the numerical. I am sure you have tried with the calculation for this numerical. So, here as we have discussed, we are having say flight condition as Mach 2.04 at altitude of 8000 meter, where our temperature and pressure are 236.23 Kelvin and pressure as 36.651 kilopascal. And we are considering same afterburner operative condition as 1700 Kelvin with 5% pressure drop and 95% efficiency. So, here we would like to do the calculation for the flight condition. In previous numerical we have done the calculation with the operation of afterburner on ground condition. So, we have done our calculation for all the parameters, the cycle parameters which are say temperature and pressure at the exit of different components, say intake, LP compressor, HP compressor, combustion chamber, HP turbine, LP turbine, afterburner, nozzle condition, and we have done our calculation till say what will be the exit velocity from the nozzle. Now, today we would like to do the calculation for say performance parameters. So, let us start with the equation for the thrust. This thrust equation, as we have discussed in a previous class, it is given by m dot infinity into 1 plus FAB into V9 minus V infinity plus P9 minus P infinity into A9. Here in this case we know what is the value of m infinity. We have done our calculation for the fuel air ratio for the combustion chamber. We have done our calculation for the fuel air ratio for the afterburner. We know what is our exit velocity. Now, since this is what is my flying condition, so V infinity also is known to us. We have done our calculation for the critical pressure ratio and we found the nozzle to be choke nozzle and this P9 is equal to the critical pressure. But here in this case the area of the nozzle, it is not known to us. So, based on our fundamental equation, continuity equation, we can do the calculation for the nozzle exit area. So, m dot, it is given by density into area into velocity. Here in this case, since the exit condition is different, so we need to do the calculation for the density at the exit of the nozzle. So, that is given by P9 by R39. Now, this P9 we have already calculated, T9 also is known to us. So, we can say density is coming to be 0.1692 kg per meter cube. Let us put this number into our area calculation. So, we know what is my m dot infinity, we have our FAB and all the parameters known to us. So, let us try to put these numbers, and if we are putting this number, it says my area is coming 2.604 meter square. So, you can look at the number, we will compare this in the next slide, but just look at these numbers. Now, what we have is our thrust equation. For the thrust equation, as we have discussed, we know all the parameters, we have calculated our area also. Let us put all these numbers together, and if we are putting this number, it says thrust is coming to be 136.81 kilonewton. Okay. Now, next parameter what we want to calculate is say thrust specific fuel consumption. Same way, now you are expert enough to understand, it is given by F plus FAB into m dot divided by thrust, and if we are putting all this number, it says my thrust specific fuel consumption is coming to be 0.0922 gram per Newton second. Now, let us calculate the propulsive efficiency. This propulsive efficiency, it is given in terms of thrust into V infinity. Since we have this as our flying condition, means we know what is our flight velocity. Based on that, we can do the calculation for the propulsive efficiency. In earlier numerical, we have done calculation for the ground condition, and that is the reason why V infinity was coming to be 0. So, be careful about this. Here in this case, if we are putting the number, it says propulsive efficiency is coming 97.58%. Okay. Now, let us calculate the thermal efficiency. The thermal efficiency equation, we know it is T into V infinity plus 1/2 mV9 minus V infinity square divided by the amount of fuel what we are adding, or we can say this is our heat energy. So, if we are putting all these numbers together, it says the thermal efficiency is coming as 15.52%. The parameter what we know is thermopropulsive efficiency or overall efficiency, that is thermal efficiency into propulsive efficiency. We know propulsive efficiency and thermal efficiency, that says overall efficiency is coming to be 15.14%. So, I am sure now you are able to understand, you are able to do the calculation of these three efficiencies: propulsive efficiency, thermal efficiency and overall efficiency. Let us put this all together. It says we are having a flying velocity, it is known to us, temperature, pressure at that flying condition, they are known. We have done our calculation for the exit area, we have done calculation for the thrust specific fuel consumption, propulsive efficiency, thermal efficiency and overall efficiency. Now, let us try to look at what all we need to understand is our performance parameter for this engine. We know this performance parameter, it is in terms of thrust or specific thrust, specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency and overall efficiency. We have our cycle parameters like my compression pressure ratio, we can say overall pressure ratio, that is what is a combination of LP compressor pressure ratio and HP compressor pressure ratio, since we are discussing about the two spool configuration. The effect of turbine entry temperature, the efficiency of different components. We are here discussing about the flight condition, so we will be considering the flight altitude, what is the effect of afterburner temperature and flying speed. So, let us take one by one. So, very first parameter we will be taking, say we will be putting our say HP compressor pressure ratio and turbine entry temperature to be constant, and we will be varying our LP compressor pressure ratio. In other means, we can say we are changing our overall pressure ratio, because we are putting our HP compressor pressure ratio to be constant. So, if this is the case, here we can say by changing my LP compressor pressure ratio, basically we are changing our overall pressure ratio, and that is what will lead to give the reduction of the thrust. So, again and again, if you try to recall, we have discussed about this point in previous numerical also, in week 3 also we were having very good discussion about this point. This is representing by increasing of our overall pressure ratio for the fixed turbine entry temperature, we will be having reduction in the thrust. This thrust we are also discussing in terms of specific thrust, that is thrust divided by m dot infinity. Under that condition, it says with the increase of thrust, the specific thrust is say also decreasing. Okay. Now, we have our parameter called thrust specific fuel consumption. So, in line to what all we have discussed, here in this case we will be having say amount of fuel which is required to raise my temperature to turbine entry temperature, that is what is lower, but at the same time we are having the drop of thrust, that is what is very high, and that is the reason why with increasing our overall pressure ratio, the specific fuel consumption is going to be increased. Okay. Now, here in this case, this is representing the thermal efficiency, overall efficiency and propulsive efficiency. We know all these efficiency parameter, they are mainly the function of thrust and the amount of fuel what we are adding. It says my fuel air ratio. It is also being affected by what will be our exit velocity. So, here we can say by increasing the LP pressure ratio, LP compressor pressure ratio, we are having drop of thermal efficiency. We will be having say drop of propulsive efficiency after certain value. Before that, if we look at, we are having our propulsive efficiency to be nearly constant, and that is what is impacting on our overall efficiency. Okay. Now, in line to what all we have discussed earlier, let us try to change the HP compressor pressure ratio, putting my LP compressor pressure ratio and turbine entry temperature to be constant. So, here in this case, in line to what all we have discussed for the previous parameter, though we are changing only our HP compressor pressure ratio, the effect will come to be same. It is increasing our overall pressure ratio. Here in this case, since we are increasing our overall pressure ratio for particular turbine entry temperature, our curve, that is what is moving more towards the left hand side, and that is the reason why the amount of fuel required in order to raise the temperature will be lower. That is one case, and V9 what we are discussing, that is going to be lower in this case. So, here it is representing the specific thrust. We can say this is what is a representation of thrust specific fuel consumption, and in line to what we have discussed for the previous case for the variation of LP compressor pressure ratio, similar trend we are getting here. Okay. Now, the scenario is the impact of turbine entry temperature, that also need to be realized here. So, for that let us take say effect of turbine entry temperature, we will be putting our overall pressure ratio to be constant. So, here in this case if we look at, this is representing my design point, and it says if we are increasing our turbine entry temperature, we have a rise of our V9, we are having increase of our A9, and that is what will lead to give the increase of our thrust. Since my thrust is increasing, that is the reason my specific thrust also is going to increase with the increase of turbine entry temperature. Now, you can put the plot for thrust specific fuel consumption. Let us see how much you have understood here. Let me give you a hint. In order to raise the temperature, basically you need to add the amount of fuel. Then only you will be able to raise the temperature from 1200 Kelvin to say 1500 Kelvin or 1700 Kelvin. So, you can say if that is the case, we can say our thrust specific fuel consumption, that is what will lead to decrease here. Okay. So, again and again I am putting this point because our next target will be on say specific fuel consumption. So, during 60s people, they are having understanding to raise the thrust requirement. They were not bothering of anything in terms of what is the amount of fuel it is been consuming. Okay. With the maturity of the technology, with the understanding, people they slowly move towards the next parameter, they started talking about the fuel economy, but till that they were having only understanding in terms of how to increase the thrust. Okay. Now, here in this case we have the parameter called thermal efficiency, my propulsive efficiency and overall efficiency. So, you can say with the increase of turbine entry temperature, we are raising our thermal efficiency, that is what will lead to increase the propulsive efficiency and we have rise of overall efficiency. Now, let us try to look at the next parameter. We say we have our turbine say entry temperature. In line to that, let us try to look at say afterburner exit temperature, that is what we want to be higher. Here in this case it says when we are increasing our afterburner exit temperature, we are able to increase the thrust. But be careful, this increase of thrust, that is what is at the cost of amount of fuel we are adding in afterburner. So, if we say this is our design condition, this is the situation, it is for the specific thrust. Let us see how you have understood in terms of specific fuel consumption. So, if we are putting this curve, it says by increasing the afterburner exit temperature, the specific fuel consumption, that is what is going to be increased. And as we have discussed, in order to achieve this higher afterburner temperature, we need to add more amount of fuel in afterburner, and that is what will lead to increase the fuel consumption. Okay. Now, let us try to look at what is happening with our efficiency. Here in this case it says when we are increasing our afterburner exit temperature, the thermal efficiency and propulsive efficiency, they are going to be reduced, because that has direct impact in terms of my fuel consumption, that has direct impact because of my thrust. Okay. Now, let us try to look at what is happening with the nozzle area. Since my amount of fuel what we are adding, that is increasing, in order to handle that mass flow rate, you need to have your nozzle area to be larger. Okay. Now, exit say the effect of the air mass flow rate, that also we can say this is representing with the increase of the mass flow rate, entry mass flow rate, we will be having the rise of thrust. Same way, if we are talking about the specific fuel consumption, it has not much impact on specific fuel consumption. Just try to correlate how this mass flow rate it is affecting the thrust specific fuel consumption, or why we are not having much impact on thrust specific fuel consumption. Okay. Same way here in this case, the efficiency, that is what will remains constant. All my propulsive efficiency, thermal efficiency and overall efficiency. And we know since we are increasing our mass flow rate, we have increase of our nozzle area with the increase of mass flow rate, or we say air mass flow rate. Okay. Now, here we have other kind of scenario. The scenario is we are considering, or we have done our design condition as say 2.04 Mach number at particular altitude. Let us try to understand how it is being affected by the flight Mach number. If we are putting turbine entry temperature, my overall pressure ratio to be same. Okay. So, under that condition, it says when we are increasing our flight Mach number, the thrust, that is what is going to be increased, but here somewhere we are having our design condition. So, you can say initially I will be flying at subsonic Mach number, and as per the requirement we will be moving towards say higher and higher Mach number, and this is with the operation of afterburner. Okay. Similarly, here in this case, if we consider this is representing my specific thrust. So, we need to be very careful here. This specific thrust, it is nothing but it is a function of thrust divided by our m infinity. This m infinity, it is a function of, we need to be careful about, it's a function of density into area into velocity. Now, since our velocity, that's what is increasing in this case, because my flying Mach number is increasing, and that's the reason why my specific thrust is going to be reduced. So, my density, my pressure, my temperature and my velocity, they all are changing. That's the reason why specific thrust, that's what is decreased with the increase of flight Mach number. Now, in terms of the specific fuel consumption, we can say with the increase of our flight Mach number, the specific fuel consumption will be increasing. The reason we can realize, in order to achieve this higher speed, we need to have the higher amount of fuel need to be added with. Okay. Now, here this is representing the change of my thermal efficiency, propulsive efficiency and overall efficiency. So, here it is interesting to observe, with the increase of flight Mach number, our propulsive efficiency is going to be increased, and that is what will lead to give the overall efficiency to be higher. Okay. Now, let us look at what is happening with the nozzle area. This nozzle area, if we look at, with the increase of flight Mach number, we will be having the change of my area. So, here this is what is representing when I am flying from subsonic Mach number towards a transonic and towards a supersonic speed, my area need to be changed, and that will be handled, as we have discussed in the class earlier, by say adjustable nozzle. Okay. Now, here we will try to compare the two different scenarios. This is what is very important. We have discussed in this week the ground condition with afterburner in operation, and cruise condition with operation of afterburner. So, here in this case, if we look at, we are having our flight Mach number, that is what is 2.04. The temperature and pressure, they are different, because we are discussing the cruise condition at 8,000 meters height or altitude. Here, if we try to compare the exit area, you can say it is 0.95 for the ground condition. For the cruise condition, this area is coming to be 2.60. Let us compare the thrust. If we are comparing the ground thrust, and if we have afterburner, it is operational, the thrust is coming as 157.8 kilonewton, but in the cruise condition it is 136.81. Same way, under the cruise condition, our specific fuel consumption is coming to be higher, but the benefit what we are getting is in terms of increase of propulsive efficiency, we have increase of thermal efficiency, and we have the overall efficiency, that is coming as 15.14. So, let us try to understand what is happening when we are discussing about the ground condition as well as under the cruise condition, in terms of change of different parameters like pressure ratio, turbine entry temperature, afterburner temperature, and then we will be discussing about what is the impact of mass flow rate. Okay. So, let us see, very first parameter we are considering, we will be changing the LP compressor pressure ratio and HP pressure compressor ratio, and turbine entry temperature we will be putting to be constant. So, here in this case we have two different conditions. This is representing my ground condition and this is representing my flight condition. So, for both the cases we have done our calculation. This is representing our design condition. For that design condition, we can say under the flight condition the thrust will be lower. At the same time, it is interesting to observe, it is permitting us to go for the calculation of LP pressure ratio in the range of maybe 9.2, or maybe we can move towards 10. But at the same time, when we are considering the flight condition, That is not the scenario. Now, this is very important for us to realize the reason, what is the reason why we are not having, say, LP pressure compression ratio to be more than some number, say 4.5 or so, because overall pressure ratio we cannot move beyond certain number. Okay. At the same time, if we are looking at, say, lower pressure ratio or lower overall pressure ratio, our thrust value is, in compared to ground condition, it is coming to be higher. Okay. And here this is what is in relation with our condition for m infinity. This is what is in relation with our exit velocity. This is in relation with our exit pressure. Okay. Same way here, in this case, this is representing our specific thrust value. The specific thrust for the flight condition is coming to be lower. Same way, if we are comparing our specific fuel consumption for the design condition or for both the calculation at the ground condition and the flight condition, my specific fuel consumption for the flight condition is coming to be higher. Okay. So, you can easily find the reason. What could be the reason for that? Here in this case, this is representing, say, our thermal efficiency, overall efficiency and the propulsive efficiency. So, as we have discussed, my operating pressure ratio is not beyond certain numbers. So, you can make your calculation, you can try increasing the LP compressor pressure ratio and just try to find what is the reason why we have not put these numbers here. You will realize the reason. What could be the reason why it is not happening? It is violating our second law of thermodynamics. Okay. So, just try to do that calculation and just find what is the reason why we have not kept these numbers there. Okay. Same way, let us look at with the LP compressor pressure ratio variation, putting my LP compressor pressure ratio and turbine entry temperature to be constant. So, here in this case also we are having similar kind of trend for both thrust, specific fuel consumption, and in terms of our efficiencies, overall efficiency, thermal efficiency and propulsive efficiency. Okay. Now, let us look at what is happening with the turbine entry temperature, because it is something that is what was not favoring in terms of understanding for flight and ground condition. Let us try to understand what is happening with the turbine entry temperature. So, here in this case, if you look at what it says, by increasing the turbine entry temperature, we are able to increase the thrust both for the flight condition and the ground condition. Okay. So, you must be realizing what all we have discussed in our week 3, what is the effect of change of pressure ratio, what is the effect of change of turbine entry temperature, how my cycle exit pressure, that is what is affecting our performance, that also you will be realizing here. Okay. Here in this case, this is representing the specific thrust. So, specific thrust for the flight condition, we can say it is lower. Similarly, we can say our specific fuel consumption for the flight condition is going to be high compared to our ground condition. And here in this case, this is representing our efficiency terms in terms of propulsive efficiency, thermal efficiency, overall efficiency. And it is interesting to observe for this case, when we are putting our pressure ratio to be constant, our propulsive efficiency, that is what is remains nearly constant. Okay. Now, let us look at what is happening with the afterburner exit temperature variation. So, here in this case, it says my thrust will be coming to be higher for the ground condition compared to my flight condition. The reason, it can easily be understood what we mean by flight condition, what will be my exit or entry pressure, what will be my entry temperature, and how it will be affecting with my overall pressure ratio, and how it is affecting our exit velocity calculation, and that is what will be impacting on our thrust calculation. Okay. Now, here this is representing the specific thrust. So, if we compare, if we are having our afterburner exit temperature to be higher compared to our flight condition, the specific thrust will be higher for the ground condition, and this is representing the specific fuel consumption for the flight condition. And here in this case, this is representing the propulsive efficiency, overall efficiency and thermal efficiency. So, if we look at carefully, it says by increasing the afterburner exit temperature, propulsive efficiency, that is what will be reducing, and that is what will lead to reduce the overall efficiency. Okay. And this is representing our nozzle area, and it says for the flight condition the area requirement, that is what is higher. So, we have done our calculation. So, this is all that is related with the selection of these cycle parameters. Okay. And this you can do calculation by making your own code, or as I have discussed, you can use the freeware software available by Mattingly. Maybe you can go with say NPSS, or maybe you can use desktop software for the calculation. So, that is what will be building your confidence. Okay. So, in overall we can realize here that afterburner operation, that is what is of need. Why we are looking for afterburner operation is to increase the thrust. Now, in order to increase the thrust, we say we will play with the parameters like our pressure ratio, overall pressure ratio, turbine entry temperature, say afterburner temperature, maybe we can play with the mass flow rate, but we have realized the effect of some of the parameter, mainly increase of overall pressure ratio, that has say inverse impact on the thrust generation. It says by increasing our overall pressure ratio, it is not favoring in terms of increase of the thrust, but that is with particular number for the turbine entry temperature. Suppose if I will be considering say for this numerical what all we have solved, there we have taken our turbine entry temperature to be say 1200 Kelvin. Again and again let me explain here, say if we are going with the turbine entry temperature to be higher, our scenario will be different. There in combination with the change of overall pressure ratio, the scenario will be different. This is all we can realize if we are putting our plot for TS diagram. So, that is the reason why it is preferred you use pen, paper and just try to plot the TS diagram. If possible, then you do your calculation for the scenario. So, all this what we are discussing in terms of effect of different parameters or different numbers in terms of overall pressure ratio, HP compressor pressure ratio, LP compressor pressure ratio, turbine entry temperature, that is what is fixed for this particular numerical. Okay. So, I am sure you are able to understand what we are discussing in week 4, and dedicatedly this has been designed for operation of afterburner. So, here in this case we are having say initial discussion with the operation of afterburner. We have discussed about what we mean by afterburner, what is the need of afterburner, and you will realize the afterburner we are looking for increasing the thrust. Okay. And then later on we have realized in order to increase that thrust, we need to compromise somewhere in terms of fuel consumption, because in order to operate the afterburner you need to put lot of fuel, and that's what will be restricting our envelope. Okay. So, here we are stopping with week 4. I am sure you are able to understand the turbojet engine and its operation. In now next lecture we will start discussing about say next kind of ADA engines, next variant of engine, and that's what will be with the different thought process. So, what I feel at this moment for all of you to please go through week 3 and week 4. That's what will be giving you more confidence and more understanding what we will be discussing in week 5. So, thank you very much. See you in the next week.